I'd like to thank the organizers for the invitation and thank you all for showing up. I changed the title of the very last minute so it'll be a little more self-explanatory, but the content is the same. This is work I've been doing over the last 3 years or so together with Christian, Natasha, and Raja. And I should mention also competing and related work by the Indian group, mostly Indian group and mostly MIT group here. So the main player in this talk is going to be entropy. You're all familiar with the second law. A process like this mostly is something that is allowed, and a process like this is not allowed, and we quantify this by saying that the total change in entropy has to be non-negative. Now this formulation of the second law is a global formulation. It says that the total entropy cannot decrease, and according to this, I can imagine some gas that fills our entire universe and have some process where I have a total entropy decrease in this region and a total entropy increase in this region, so that the total entropy is going to be non-negative, and then an observer here would say, oh, look, I have negative change in entropy here. Now, this, of course, if we really think of the second law as a global law, then something like this is allowed. We know that it's not, and there's a way to formulate a local version of the second law, at least when we're in configurations which are close to equilibrium. This is not something new. You can find it in Landau-Lifshitz. And it goes, the local version of the second law is something like this. We look at some region in space. We ask about the total change in entropy in this region, and we can talk about a total flux of entropy leaving this region, and the local version of the second law is a statement that this quantity has to be non-negative. This can be written in a differential form. We have a current which we call the entropy current, and we demand that this entropy current is non-negative everywhere. And in order to say that this is really an entropy current, we say that in equilibrium, meaning when gradients of thermodynamic quantities can be neglected, then this entropy current should be the entropy density. Its zero component should be the entropy density, and its spatial components should be zero, as long as we're in the rest frame of whatever system we're looking at. So these two qualities define the entropy current. So the entropy current is the thing that does 1 and 2 here. And it turns out that you get a lot of mileage just by acquiring these two requirements. So first thing, and this is what's going to be important in this talk, is that it can constrain transport. So you can use this to show that, for example, the conductivity or the viscosity have to be positive. So positivity or non-negative. This can follow from positivity of the divergence of the entropy current. Again, this is not something new. This is something that you can find in Landau-Lifshitz. There are certain transport coefficients which are constrained by this positivity. There are certain transport coefficients which have to vanish by this requirement. And when people write down effective hydrodynamic theories or extensions of hydrodynamic theories, then what one does is usually write down the most general equations that one can write down that are compatible with conservation laws of the theory. And then on top of that, require that the second law hold, and that constrains the equation, gives also constraints on transport. And this is sort of a phenomenological model of hydrodynamics, whereby one assumes these are all the constraints that one should put into the theory. There's also an interesting interplay between this local version of the second law and various things one sees in ADS-CFT in relations to black hole entropy. This is something I'm interested in, but I'm not going to talk about today. So this is something that works pretty well, but there are open ends here. The first question is whether this local version of the second law really exists. I mean, we have some statistical mechanics method of talking about the second law, but something like this is kind of strange, especially if we look at it from a field theory perspective. We know how to write down quantities that are conserved, but how are we going to get from an effective theory some current whose divergence is non-negative? There should be some mechanism that'll give us that, and it's unclear how to get it. And the second question, or the second open end here, is, again, when applying this local version of the second law to things that are close to equilibrium, to hydrodynamics, then one gets certain constraints on transport. But again, this is sort of something that's being done by hand. There's no real rule that says that these are the only constraints and then there aren't any more. So the question is whether this is sufficient to fully constrain the system, whether the second law is sufficient to fully constrain the system or not. So what I'm going to do is try to address these questions. And I'm going to use Schwinger Keldysh effective theory to address them. So most of the talk, I'm going to devote most of the talk to describe how to write down an effective action for Schwinger Keldysh theory. There's some delicate points there that'll be important for answering these questions about the entropy current. Then I'll tell you about how to derive the entropy current from Schwinger Keldysh effective theory. What will happen is that in order to write down an effective action for Schwinger Keldysh theory, one needs to add some fictitious coordinates, and the entropy current is conserved in the real space plus these fictitious coordinates. And once one looks only at the conservation law for the real space, the part really becomes the non-conservation of the entropy current, and one can show by unitarity that that has to be positive. So this is sort of the punchline for the entropy current. And then I'm going to show that there are constraints on hydrodynamics, there are constraints on transport that are not captured by the entropy current, and one needs full machinery of Schwinger Keldysh effective theory to actually see these constraints. So let me just remind you about Schwinger Keldysh theory, at least from the perspective of field theorists. So you're all familiar, I think, with the generating function of connected correlators in the vacuum. If we want to find out an endpoint function of some theory in the vacuum, we take this object, the partition function, and we vary its log n times with respect to a source, and that gives us the endpoint function of the current, of the associated operator. Now, we can also do the same thing in thermal equilibrium. We can ask for the endpoint function of some operator in thermal equilibrium, and it turns out that that's given by n variations of Schwinger Keldysh partition function. So I'm just reminding you the Schwinger Keldysh partition function gives us thermal expectation values of correlation functions. Let me be a little more precise. What we get here is actually time-ordered correlation functions. And what we get here is slightly more involved. So the Schwinger Keldysh generating function actually has two sources for each operator. Okay, so here we have one source for each operator. The Schwinger Keldysh generating function has two sources for each operator. And if we vary it n plus m times with respect to the two sources and set them equal, what that'll give us is a thermal expectation value for m anti-time ordered operators and n time ordered ones. So Schwinger Keldysh theory does two things for us. It gives us thermal expectation values, and it also gives us anti-time ordered and time ordered, or this particular product of ordered endpoint functions. And with this, we can actually compute various Green's functions, not only retarded ones. If we define the sum and difference of the sources in this particular way, then it turns out that this will give us the symmetric Green's function. This variation will give us the retarded Green's function. This variation will give us the advanced one, and the remaining combination will just give us 0. The fact that this is 0 is going to, I'm going to explain why it's 0 in a bit. It's actually important for construction. Okay, so this is what the Schwinger Keldysh generating function does for us. We can write the partition function as a functional integral of this form. The Schwinger Keldysh generating function can also be written as a functional integral, and it looks something like this. So because we have two sources for each operator, we essentially look at the difference of the actions, and there's an initial condition at t equals minus infinity, where maybe I can just use the microphone. No, it's in, but it's on airplane mode. So, will it work now? Better? We'll see. I'll put this on right here. Okay. Yeah. So we can write the generating function of connected correlators in the vacuum via a functional integral, and there's a similar functional integral for the Schwinger Keldysh generating function. There's a more formal way of writing this expression, which looks like this. So U is the time evolution operator in the presence of a source A1. U dagger is its inverse in the presence of a source A2. And this is sometimes more useful to write than this. Now, often we look for an effective theory. What that means is that we're looking for an effective action such that when we integrate it this way, we get the generating function at low energies. What we want to do here is find an effective action that'll reproduce the Schwinger Keldysh generating function at low energies. So I'm going to assume that I can integrate out all the fast modes and get an effective action for Schwinger Keldysh theory. Now I'm not going to do this explicitly. What I'm going to do is assume it exists and then see what are the symmetries that it should have. I'm going to make a guess about the degrees of freedom and then just write down the most general effective action that I can that's compatible with the symmetries and those degrees of freedom. And we'll see that that's going to reproduce essentially hydrodynamics with noise. Okay, so what are the symmetries that we need? Well, first thing we need is essentially a doubled set of symmetries for the sources. So let's imagine that this is a source for A1 and A2 are sources for gauge fields. Then if we make a gauge transformation of A1 or we make a gauge transformation of the second potential A2, then the Schwinger Keldysh generating function shouldn't change, assuming there are no anomalies. So whatever action we put in here, it should have double the amount of symmetries of the original theory. Okay, so if we have coordinate invariance, if our source is a metric, so the metric is the source for the energy momentum tensor, if we want this partition function to reproduce correlation functions of the energy momentum tensor, we need two metrics here, and whatever action we put in here, it should be invariant under coordinate transformations of each metric separately. So this is one symmetry we need. The second symmetry is something that I call Schwinger Keldysh symmetry. If I set both sources to be equal, then, well, by cyclicity of the trace and unitarity, this is just going to be 1, assuming everything is properly normalized. And well, we'll see the implications of this in a bit. So this is something else that we need that the effective action will do for us. The third symmetry, or symmetries, are reality and positivity. So the partition function for vacuum correlators has to be real. It turns out that the Schwinger Keldysh partition function doesn't have to be real, but it should satisfy some reality condition of this type. Usually the sources are real, and then this equation just says that the complex conjugate flips the two sources. There's another condition that needs to be satisfied, which is a positivity condition. And again, this follows, there's a few lines here. It takes a few lines to show it, but this is another constraint that the Schwinger Keldysh generating function has to satisfy. It follows from unitarity of the time evolution operator. Last condition is called the Kms condition. I'm sure you've all seen it. When you look at 2-point functions of operators in a thermal state, one can think of e to the minus beta h as time evolution in imaginary time, and it relates operators at when they're shifted by imaginary time. So one can make the same sort of analysis for the partition function, and what one gets is that the partition function has to be equal to this shifted partition function. Eta A1 and eta A2 are just CPT eigenvalues of the operators that are conjugate to these sources. So if the operator changes sign under CPT plus or minus 1, then this eta is going to be plus or minus 1. So these are the symmetries I want to impose. I want to impose it in such a way that the effective action will ensure that these things are satisfied. So these are the symmetries. The next thing I need to figure out are what are the degrees of freedom. And here I'm going to have to guess, because there's no way of sort of deriving it unless I actually integrate out, and I don't know how to do that. And I also don't want to do that, because I want to get something that'll give me information about, of a theory. I want something that's theory independent. I want to make a statement about any sort of action that I put in. I want to get its low energy description, and I expect the low energy description to be universal as long as the thing becomes hydrodynamic at low energies. So all the theories that are going to be hydrodynamic at low energies, they essentially are going to flow to the same effective theory, maybe up to some changes in actual values of transport properties or constitutive or thermodynamic relations. So the degrees of freedom have to be such that I'm going to reproduce hydrodynamics in this low energy description, and I have two motivations for the degrees of freedom I choose. One has to do with how one describes fluids. So there's Euler's description of fluids, which says that at every point in space we define a velocity field and a temperature, and we see how those change at that point in space. Everything I'm going to talk about is relativistic, but almost everything I say has been generalized in a non-relativistic context. So I have a 4 velocity here, which tells us how the fluid is moving, and a temperature, which tells us essentially a temperature field, which tells us the temperature at every point in space. Now there's an alternative description of the fluid. It's called the Lagrange description, where I essentially keep track of fluid elements. So I have some coordinate big X, which tells me where each fluid element is located, and it has a label, which I'm going to call sigma vector. It's the label that tells me which fluid element I'm looking at, and there's some internal time, sigma naught, which tells me how this thing is flowing. So if I want to keep track of this element, it's going to look like some line here. So using standard terminology in high energy physics, I'm going to call this is the real space where the fluid lives. I'm going to call it a target space. And this thing is a world volume. It's some fictitious coordinate system which allows me to keep track of fluid elements. And this X is essentially a mapping from this fictitious coordinate system to the real space, from the world volume to the target space. So my degrees of freedom are going to be these embedding functions, these X's, which keep track of fluid elements. There's another reason for using these degrees of freedom for using these degrees of freedom, and that has to do with the fluid equations of motion. So the fluid equations of motion are essentially energy momentum conservation. And what we want is that, at least classically, the equations of motion for our dynamical degrees of freedom are going to reproduce energy momentum conservation. So if we have an action which looks like this, So the action lives in this sigma space, in this world volume, and it's a function of a metric Gij, which is this combination of G mu nu. It's called the pullback of the metric. It has some geometric properties. What's nice about it is that it's essentially invariant under coordinate transformations in the in real space, in the target space. So you see all the mu nu indices are contracted. So it's really a scalar in the target space. It doesn't transform like a tensor. It's like a scalar. And if we use this action, then one can show that the variation of this action with respect to x, which should give us the equations of motion, is going to look something like this. So the equations of motion for this x coordinate are really energy momentum conservation, and that's what we need in order to really have fluid dynamical equations of motion following from our effective action. So these are the symmetries. These are the degrees of freedom. Here, remember, we need to double all our sources. So if we want to talk about, again, something that will give us correlation functions with the energy momentum tensor, we really need two metrics. So we really need two of these functions. So you can imagine that we have one sigma space and two functions which bring us into both these target spaces, both these metrics. Of course, at the end of the day, after taking variations, we identify both the metrics. There's really only one metric in our world. Okay. Sometimes I'm going to switch from x1 and x2 to x1 minus x2 and x1 plus x2. Again, this is something standard in Schwinger Keldysh theory, and it turns out to be useful when writing out the action. So let me show you the end result. I don't really have time to derive everything, but the end result is an action which looks like this. So this holds a lot of information. Let me try and explain what the elements here mean. So L tilde comes from this Kms symmetry. So remember, Kms symmetry, the fact that the initial state is thermal equilibrium, is a statement that this partition function is equal to this one. And you can see that this is a Z2 symmetry, by which I mean if I apply it twice, I end up where I started with. So I need some transformation of this action that I apply it twice, I get what I started with. So the easiest way to do that is just to take this, whatever Lagrangian we have here, act on it with this type of transformation, and just add it into our action. So now if I act on this action with this transformation, L is going to go into L tilde. L tilde is going to go into L again, because this is a Z2 transformation. It goes back into itself after we act on it twice. So that's this L tilde. It ensures the Kms symmetry. These theta coordinates are really what's going to be important when we talk about the entropy current. So they come from this requirement that if you remember, unitarity forces the Schwinger Keldysh partition function to be 1 once the sources are aligned. So remember, we talked about a sum and difference of sources. So in this language, the Schwinger Keldysh partition function becomes 1 once the difference between the sources are 0. And that means that if we take any sort of variation of this type, we're going to get 0. This is somewhat surprising because we have two sources. We're essentially getting rid of one. We expect to have a partition function which depends on one source, but it doesn't. It doesn't depend on the sources at all. So this is reminiscent of something called a topological symmetry. So in a topological symmetry, in a field theory context, we say that a theory is topological if correlation functions don't depend on the metric. So here, the source doesn't have to be the metric, but whatever source we have, once these sources are aligned, once A1 equals A2, instead of having the theory depend on the sum, it just doesn't depend on anything. So this is there's a sector in this theory which becomes topological once the sources are aligned. Okay, so we need the action to somehow account for that. There's another way to think about it, which has to do with BRST, which would be to construct this in a BRST type of construction. I won't go into it. Both of these ways of thinking about the problem are equivalent. And there's a standard way of implementing this symmetry, what we need is a generator which is nilpotent, meaning the generator of the symmetry would square to 0. And again, I don't have the time to go into this. You're all familiar with, I guess, Chern-Simons type theories, which are topological. They don't include the metric explicitly in the action, but there's something called Witten type topological theories or cohomological theories, and those can be constructed by insisting that there's some nilpotent operator in the theory, and the action is going to be closed under this Q, and the energy momentum tensor is exact. Details aren't very important. You're going to have to just take my word for it. And to realize a nilpotent symmetry, we can use something that's called superspace. So superspace is essentially an extra fictitious coordinate which squares to 0. So it's really not a coordinate that we assign a value to. It's just some object that we add that squares to 0, and it just helps us organize things so that at the end of the day we're ensured that we have this nilpotent symmetry. So what this means in practice is that if we have these embedding functions, instead of depending only on sigma, the real space, they depend also on this funny superspace coordinate theta in this particular way. Since theta squares to 0, if we Taylor expand this, we're essentially going to get something that's independent of theta and something that's linear in theta. It's very easy to deal with these coordinates. And then the action is, if we write it this way, is guaranteed to be invariant, to vanish if we act on it with Q. Okay, so this is just a trick. Because things are linear in theta, I can essentially do the theta integral. Right? The theta is really not really a variable that I assign a value to. It's just a thing that allows me to keep track of what's going on. So if you don't like it, you can just integrate over this theta coordinate and get a standard action. But these things are going to be arranged in such a way that they'll be invariant under some nilpotent symmetry Q. The action can also depend on derivatives with respect to theta. Again, these can be integrated in an appropriate way. Okay, I hope I didn't lose everybody. So that's why we have one theta coordinate. I wrote here 2. The reason we have 2 of these coordinates has to do with the fact that these two symmetries don't form a group, right? So if we have symmetry, we can act on them we can act with it twice. We can act with each symmetries once, and we should again get a symmetry. So in order for this Schwinger Keldysh symmetry and the Kms symmetry to close, we need to add another nilpotent symmetry, which is generated by another operator, which I'm going to call Q bar. And to do that, we need an extra theta coordinate. So if before we had this, now we have 2 coordinates, theta and theta bar. Each of them square to 0. So essentially, we have 4 components here. And the action is going to take this form. And now this big d theta and big D theta bar are essentially covariant versions of theta derivatives. They take this form, and their form is such that they commute with Q and Q bar. Okay, so the details again are not very important. What's important is that we have to add these fictitious coordinates in order to have this Schwinger Keldysh symmetry, to have the sector which is topological when the sources are aligned. Okay, so this is what we have. Let me write the action explicit. Let me give you this Lagrangian L in a little more explicit form. So the Lagrangian L is going to take this form G. This G is essentially a superspace version of the G I showed you before, the pullback I showed you before. We take G1, we contract it with dix1 djx2. dix1 djx1, same thing 2, and we just arrange them into some sort of object which depends on the theta and theta bar coordinates in an appropriate way. There's some fine print here which I'm not going to go into. It can depend on covariant derivatives of these objects, and again, these are covariant derivatives with respect to this metric which has both sigma coordinates and theta bar coordinates. Beta I is essentially the temperature of the initial state. It's a vector that's pointing in the time direction, and its size is beta. and d theta bar are the derivatives I talked about before. I'm going to swap this with something a little more formal. This L beta is something that's called a Lie derivative. It essentially tells us that we have to translate along curves of equal Euclidean time. So I'm just going to write Lie derivative here, and when this thing acts on scalars, it's just a directional derivative. It's a derivative in the thermal direction, in the time direction. This I is here comes together with the fact that this Lagrangian has to be real, and this is a result of having this reality condition. There's one more condition that needs to be imposed, and it's an important condition. It's the fact that this action, the imaginary part of this effective action, has to be non-negative. This comes out from this constraint, which follows from unitarity. Okay. So this is what we have. Let me show you an example just to show you that this is not all in the air. I can actually write down an action. So let me take the simplest action I can write down. This is the simplest action I can write down in the sense that I've ignored any derivatives of the quantities g. So the action depends on g and its derivative. And I just said, okay, let's pretend we don't have any derivatives of this g. So I need something that's invariant. So I need the object here must be a scalar. So the only scalar I can construct out of this g and beta is this one, unless I include derivatives, and I don't want to. And so p is some arbitrary function of this only single scalar quantity that I can write down. So this is the sense in which this is the simplest action I can write down. And now I can compute the equations of motion and see what I get. So the equations of motion are some sort of conservation law for an energy momentum tensor. And what one finds is this energy momentum tensor. So epsilon is the derivative of p with respect to its argument. I can identify this ui with the direction with the thermal time direction, and it squares to -1. So this is the energy momentum tensor of an inviscid fluid in a relativistic system. So what we put in is the most general thing that we can write down that doesn't have any gradients. And what we got is essentially the energy momentum tensor of an ideal fluid, which means that we ignored gradients of the velocity or the shear tensor or any other gradients in the theory. We can look at something slightly more involved. We can add something that looks like this. So here I added these superspace derivatives of the metric. And if you work out the details, what you'll find is that this gives an energy momentum tensor, which looks like this. Sigma ij is the shear tensor, is essentially the symmetric derivative of the velocity field, and eta is the shear viscosity. Okay, so this reproduces the equations of motion that follow from this action reproduce the hydrodynamic equations. And this was actually an open issue, how to write down equations of motion for systems which are for relativistic hydrodynamics which are viscous. So this gives us that. How am I on time? 5 more minutes. Okay. So and now I can explain what happens with the entropy current. So we have this effective action, we have this Lagrangian, and now we want to write down the entropy current that's associated with it, or find something that'll enable us to get the entropy current. What I want to note is that the anti-commutator of these two nilpotent symmetries gives us a thermal translation. And what I want to do is find the current that's associated with this thermal translation. So let me start with a toy model. Imagine that we have just a scalar field, standard scalar field and metric in some space. A general variation of both the field and the metric will give us something proportional to the equations of motion times the variation of the field, and something proportional to the energy momentum tensor times the variation of the metric. And I'm assuming that there are no boundaries here, so all boundary terms just drop off. Now, a transformation of this type is not necessarily a symmetry. if I translate the scalar field along the time direction, and I also translate the metric along this thermal time along some time direction or along any vector field, it's not necessarily a symmetry. But what I can do is consider a gauged version of this transformation. So what I mean by that is, instead of this transformation, which is just a translation along these vector fields, I consider a gauged version of it. I just add this lambda t, which is an arbitrary function of the coordinates. This is also not a symmetry, but we can make it one in the following sense. First thing we do is we introduce a connection. So anytime we gauge a symmetry, we introduce a connection. So I've introduced a connection here, which has a particular kind of transformation law. What this transformation law does is it ensures that the Lagrangian will transform in the same way as the fields under this transformation. So this is still not a symmetry. The variation of the action is not going to be 0. But I can also modify the measure. So instead of using square root of g as the measure, one can use this modified measure. And what happens when one puts all these things together is that the modified integrand inside the action is a total derivative. So that means that if we make this minimal coupling and change the measure, we're going to get that the variation of the action under this weird transformation is 0. And that means that there should be some current associated with this transformation. So if we change the action now, then we're changing the dynamical field, we'll change the metric, and we'll also change this extra gauge field that we've added. And what we get at the end of the day is that the divergence of this current that's conjugate to this extra field is going to take on this value. It's not a conservation law, but it's an identity that must hold. In case that these translations are isometries, meaning that the metric is invariant under these translations, for example, if we're talking about the Minkowski metric, it's invariant under translations. I can talk about this directional derivative along lines of constant t or lines of constant x. I'll get 0 here, and we know that anytime we have a symmetry, we get a conserved current. If we talk about translations, this will just reproduce momentum conservation. So far, this is just a complicated way of looking at conservation due to symmetries. But now we can apply it to our model. So we started with some transformation, with a gauged version of the symmetry that we wanted to look at. So here, the dynamical fields are x, and I want to gauge their transformation. Note that the metric itself is inert under translations on the world volume. The translations on the sigma coordinate, the metric itself doesn't see them. So the metric is really inert. The target space metric, g mu nu, is really inert under this transformation. Second thing I want to do is add a connection. So I need to add a connection here. But here I need to add a connection both for the regular derivatives and for these superspace derivatives. So instead of the connection having an index only in the sigma space, it also has an index in this extra superspace direction. And now I can construct a current by varying the action with respect to the source, and it gives me this conservation law. In our model, what we get is that we get some action which has indices in both the regular space and the superspace direction, and its divergence in superspace is going to give us 0. So this is sort of the main result here. I can expand this action in theta and theta bar. So the lowest component of this equation is this one. And again, because it's a finite series and it's 0, it means that each of the components has to be 0. This bottom component, the lowest component, the one with theta equals theta bar equals 0, is this equation. I can rewrite it in this particular form, which is suggestive. And now I remind you that the entropy current has 2 defining properties, which are these. And what we can show is that the current that we got has these 2 defining properties. So the first is that once we neglect gradients, it just gives us the entropy density times the center of mass velocity. And the other has to do with positivity. And again, here one can use the fact that the imaginary part of the effective action has to be non-negative in order for this to be positive. Okay, so to show this, we just use the action we used before and just compute it explicitly and show that it's given by the entropy density, which is essentially the derivative of the pressure with respect to temperature. And show this, we have to work harder. We just write the most general Lagrangian that we can, and we keep track of various terms, compute the imaginary part explicitly, compute this thing explicitly, and show that it's positive. Okay, so this is a way that we reproduce the entropy current. Positivity follows from conservation in superspace. So it's really a conservation law that's associated with some funny fictitious space, but once we move this to the right-hand side, we get something that looks like a non-conservation law, and from unitarity, we get that this thing is positive. So I don't have time to really go over the constraints one gets on transport, but one can go ahead and use this machinery to study various types of transport and show that some transport is constrained just by constraints on transport really follow from this, and sometimes it's captured in the entropy current. Sometimes there are terms here which the entropy current does not see. This arrow doesn't go both ways, and that's how we get extra constraints on transport. So I'll stop here because I'm out of time. Sorry. Sorry.
Questions, please. So do the higher moments in theta of this conservation law correspond to?
They all include A-type fields, difference type fields, and those involve noise. Those are really associated with, you can associate them with stochastic noise. So I haven't found a physical interpretation, but I think it's somehow related to what would happen to entropy production in the presence of stochastic noise. But I don't know. We haven't figured it out. They naturally vanish. Under the equations of motion, they vanish.
And you said you were also going to say something about why the lower left-hand corner of the Green's function is 0 and why that was important.
Yeah, well, that's essentially the statement that when the sources are aligned, it's 1. So it's part of that bigger structure.
So this topological property is just accidental property of the Schwinger Keldysh construction?
It's not accidental because it's in the UV. So it's, I mean, if you mean accidental in the sense that you see it only in the effective theory, then no, you see it in the UV. So it's something that exists at all energy scales.
I mean, it's just a bit find it surprising that you start from any theory which doesn't have to be topological, but in the end you end up with a topological theory.
So no, so the theory, well, again, the theory is topological only in the sense that, so again, Schwinger Keldysh theory really has, it has 2 sources. So it's not, so you have an action which is non-topological, it's fine, but if you write the generating function in the UV, it's the difference between 2 actions with different sources inserted. And the statement is that when the sources are aligned, this thing collapses and you just get 1. So this is something that you see in the UV. So it has to do with the fact, with the way, so Schwinger Keldysh partition function is really different from the original, from the vacuum generating function, in the sense that it has to do with some interplay between the 2 sources that you put in. So it's really not a topological symmetry of the UV theory, it's a topological symmetry of the structure of the generating function.
So in your effective action, the equation of state is automatically comes from the form of the action that you choose.
Yes.
Is that right?
Yes.
And can you probably comment a bit what kind of restrictions you get?
On what?
What kind of restrictions you get from
So,
from
I mean, so far, so yeah, it's kind of, so we just, what we got so far is 1 restriction. I can just show you the end result. Yeah, so, I mean, it's just an example. If you look at this energy momentum tensor, so this is the ideal part, And then you have some expression which is essentially, there's another parenthesis missing here, essentially second order in derivatives. And if you just do the standard analysis, you find that this thing is unconstrained, but Schwinger Keldysh theory will tell you that this particular transport coefficient has to vanish. So there are lots of these, but I mean, tell me, I mean, I can write down some, you know, you can just, I can look at the action and tell you which terms in the action will give you this kind of transport, which should vanish but doesn't vanish if you just use entropy current. But I mean, I can't say much more than that.
Other questions? Just wondering, back in the 80s, there was this approach practice where they would look into the fluctuations, thermal fluctuations in various, all sorts of classical systems, which was made formally supersymmetric.
Yes.
The random, I guess, driving forces
Yes.
united with the random variable
Yes.
towards
Yes.
supermultiplet.
Yes.
How close?
It's very close. So I mean, it's all. I mean, without that, probably this wouldn't have been done. The problem here is really there's a tension between doubled coordinate transformations and this topological, this supersymmetry, or I should say superspace, not supersymmetry. So there's a tension there, and there was a footnote that I just said, you know, I ignored, but there's still this tension. We can only do this in sort of in certain limits. So yeah, it's based on this formalism, Langevin equation, but there's a little more structure.